All right, so today we have Anindya Dey tell us about unitary 3D Lagrangians for Argyres-Douglas theories and an IR duality. Take it away.
Thank you. Let me begin by making some general remarks about Argyres-Douglas theories. So 4D n equals to 2 interacting SCFTs, as we know, these are with Coulomb branch operators, which have fractional scaling dimensions. Now, in this QFT perspective, Argyres-Douglas theories appear as low energy effective field theories on certain special locus of the Coulomb branch of 4D n equals to 2 Lagrangian theories, where certain mutually non-local particles become massless. And you can also read this off from the Seiberg-Witten curve by looking for points at which the curve becomes degenerate. Now, in this traditional QFT picture, the Coulomb branch of the SCFT has a more straightforward description in terms of the Seiberg-Witten curve, while the Higgs branch can be a little subtle. Can you hear me?
Yeah, you will.
Yeah, okay, there was some noise. Just give me 1 second, please. I don't know. Yeah. So what I was saying is that in the traditional QFT picture, the Coulomb branch of the SCFT has a more straightforward description. Just you can zoom in on a certain area of the Seiberg-Witten curve, look for the relevant deformations around that point, and you end up with the corresponding Seiberg-Witten curve for the Argyres-Douglas theory. But the Higgs branch of the same CFT can be a little subtle. So, for example, we know that the same Argyres-Douglas theory can be realized from 2 different UV Lagrangians, like as superconformal points of 2 different UV Lagrangians, and one of them might have a UV Higgs branch, while the other one may not. Like the classic example is that of SO2n super Young-Mills and SUn-1 super Young-Mills with 2 flavors. The latter obviously has a Higgs branch, which is C2 mod Z2, while the former has no Higgs branch. And yet they describe the same Argyres-Douglas point. So for this kind of a theory, for the SO2n super Young-Mills, the Higgs branch sort of appears quantum mechanical. So it's really right at the superconformal point where you have the emergence of a Higgs branch, but not in the UV. So then that's the reason for commenting that the Higgs branch is a little more subtle from this perspective. Now there are various different realizations of the Higgs branch of Argyres-Douglas theory. It can happen through the Seiberg-Witten curve, which was first, I think, worked out by Argyres, Mariucci, and Tachikawa in a paper in 2012, I think. And then you can use the technology of BPS quivers. And then finally, there is 3D mirror symmetry that you can use to also learn about the Higgs branches of these theories. So I won't talk about the Seiberg-Witten curve and the BPS quivers in this talk. I'll directly jump to the technology of 3D mirror symmetry and how it can help us understand the properties of the Higgs branch of Argyres-Douglas theory. All right. Okay, any questions up to this point? All right. So how do I read off Higgs branch of a 4D SCFT from mirror symmetry? So the idea is to compactify the SCFT on a circle and flow to the IR, which leads to some theory A. Now the theory A is not guaranteed to be Lagrangian. It's some SCFT with a Coulomb and a Higgs branch, but there may not be any Lagrangian description. But the 3D mirrors of A, which we call B, often does have a Lagrangian description. So this is just observation. I mean, I'm just completely talking about QFT right now. Now, if indeed B is a Lagrangian theory, then the Higgs branch of the Argyres-Douglas theory is given by the Coulomb branch of B in the deep IR. So there's some realization of the Higgs branch using a Lagrangian theory in that case. But then again, Coulomb branch is a very complicated object. I mean, it's a hyperkähler space, but not necessarily a hyperkähler quotient. So the easiest thing the easiest thing that you can think of in 3D is to have a hyperkähler quotient. And that can only happen if A itself is Lagrangian. Okay. So if A is Lagrangian, then you have the realization of the 4D Higgs branch as the Higgs branch of a 3D n equals to 4 theory. Okay. Now, the main result that I'll present in this talk is that for a very large class of Argyres-Douglas theories, A is a quiver gauge theory. A turns out to be a quiver gauge theory and can be explicitly written down given the theory B. So if you know B, you can write down A for a very large class of Argyres-Douglas theory. So in that case, what that implies is that the 4D Higgs branch is realized as some hyperkähler quotient, where the data comes from the quiver gauge theory describing A. So the strategy that I'm going to take is that I'll begin with a systematic construction of this theory B using the 4D data. And then I'll use some 3D QFT machinery to check if A can be Lagrangian and to figure out the exact quiver for A in cases that it's possible. So to accomplish the first step, I'll need to use string theory. So this is something that I'm going to describe next. So let me pause here to take questions if there are. Okay. So in string theory, there are two distinct types of construction of these Argyres-Douglas theories. One is the approach of geometric engineering, the type 2B superstring on a singular Calabi-Yau hypersurface. So Simone Giacomelli gave a very detailed talk about this last week. So for our case, there will be two classes of such theories that we will discuss later in this talk. One is the famous GG prime theories of Chakotay, Naitsky, and Waffa, where this so-called singular Calabi-Yau hypersurface is labeled by a pair of linking diagrams G and G prime of the ADE type, and the DPG theories, where G is again of the ADE type, and P is an integer. So there is this whole literature on engineering these theories from type 2B superstrings. And then on the other side, there is the class S construction, which basically proceeds by the twisted compactification of a 6D 2,0 theory on a Riemann surface with punctures. So in this case, there is something called the Hitchin field, which is used to classify, the possible, which will be very useful in what I'm going to say next. So just you can see it from the Seiberg-Witten curve itself. So if you write down the general form of the Seiberg-Witten curve for an AN-1/6D theory, for example, which is this, you can rewrite this. So Z, remember, is the coordinate on C, and X is a coordinate on T star C. You can write this Seiberg-Witten curve into what is known as the spectral curve. And the capital phi is what is called the Hitchin field. Now, the geometric data of this construction is completely packaged as boundary conditions of this Hitchin field at the punctures. So what we call a regular puncture corresponds to a simple pole for this Hitchin field phi, and the irregular punctures correspond to the higher order poles. Now it turns out that Argyres-Douglas theories, one can construct them using class S, with C being a Riemann sphere, with either a single regular puncture or a single irregular puncture, or a single irregular puncture with an additional, one single regular puncture. Okay, so this is basically the construction that allows you to construct all the Argyres-Douglas theories that we know of. There are also other constructions involving twisted 6D theories, but that's less generic in nature as far as I know.
Anindya, in case you take two irregular punctures, is this known what you get?
I think you can only have, because of the U1R, you can only take one, I think.
Oh, okay.
Yeah. It's restricted.
Two irregular will give you two U1R?
No, I mean, you have to, I mean, it's fixed by, I mean, it's, I mean, you can consider probably two collisions of two irregular punctures, but I don't see how you can have two separated irregular punctures.
Okay.
Yeah. I mean, I'm talking about the minimal sort of fixture that you can, you can probably gauge things and so on and build things. But,
I see.
Right. Okay. So Dan Shi also gave a talk here at Quiver Meeting, I think sometime last year. So he discussed this in a lot of detail. So I would refer you to that one in case you're interested in learning more about this. But what will be important for our purpose is the following. That the classes construction for Argyres-Douglas theories gives you a systematic way to construct these 3D mirrors B in this picture. So there is a clear recipe for constructing these theories B given the class S data. Okay, so how does that work? So given the class S data, which means the singularity data of the Hitchin field at the punctures, you associate to every puncture a quiver gauge theory, which can be read off from the singularity data of the puncture. And then in the second step, you glue them together following certain rules, which depend on the nature of the punctures involved. So it's just two steps. So the details are not important, sort of, so much, but it's important that what is important is that, given the classes data, there's a clear dictionary to write down the theory B, which is a 3D mirror of the Argyres-Douglas SCFT. So now what we aim to do is that given this classes mirror, can we derive, what can we say about the mirror of the 3D mirror, which is theory A? And in particular, what we want to ask is that whether A is Lagrangian or not, or can be Lagrangian or not. So we'll focus on two, we'll explicitly focus on two infinite families of Argyres-Douglas theories, but the construction can be extended to many others, as I'll indicate later in the talk. So the first one is the GG prime kind of theory, where both G and G prime are A-type, and the rank of the linking diagrams are fixed in this fashion, as you can see. And the second infinite family is a DP-SUN, where P is an integer, and P can be less than or greater than N. We'll consider both cases. So the first theory, which is the AA theory, that's realized by a single irregular puncture. While the second one is realized by single irregular and a regular puncture. Okay, so these are sort of the theories that lie in the overlap of the geometric engineering construction and the classes construction. So that's where we're operating. All right. So now I'm going to proceed to tell you what kind of a 3D QFT machinery you need to derive the Lagrangians A, given the theory B. And these go by the name of S-type operations. But before I do that, let me pause and take questions if there are any. Okay. All right. Okay. So before I discuss the 3D technology, let me discuss a little bit about the quiver notation that we're going to use. So I think this is familiar to most of you. So I designate the vector multiplets explicitly, so there will be two kinds, UN and SUN, and this is how I designate them. The only new thing probably is this thick line connecting two gauge nodes. What it means is that you have, a p number of bifundamentals connecting UN2 and UN1. And there might even be bifundamentals connecting UN and SUN and so on. So all combinations are possible. The new ingredient that will enter later on in this talk is this blue line, which I call abelian matter. So these are hypermultiplets that are charged under the U1 subgroup of the UNI gauge groups. So generally they can be, the Qs are completely unconstrained, but for our discussion, we'll only restrict ourselves to Qs, which are multiples of Ns. So you can think of them as powers of determinant of the antideterminant representation of the unitary factors. Okay, so it's a product of determinant representations. So this is the only new ingredient that we'll have, and this will play a very important role in what comes next. Okay. Is the notation clear to everyone? Okay, excellent. All right, so now we are ready to begin. So the basic question, so now let's forget about 4D and we are down to 3D. So what we are asking is that, given a quiver gauge theory in 3D of arbitrary gauge groups and matter, how do I construct its 3D mirror? Okay, so this is the question that could be just independently posed in 3D. So I, of course, cannot answer that question in complete generality. That's too difficult a question to answer. But I'll try to answer that question for a very important subclass of theories or quivers in 3D that you can think of. I call that class U. So it consists of good theories where good in the Gallardo-Witten sense. So it's a good theory where there is a subgroup of the Higgs branch global symmetry, which I call G sub, such that G sub is a product of unitary factors. Okay, so that's how the class U is defined. And I'll denote it by this gray blob X, where a UM alpha node is isolated. So X can involve, any sort of, structure inside. And all we are doing is isolating a UM alpha flavor. So that's where we are gonna, that's where all the action is gonna happen. All right. So given a generic quiver of class U, I'll define 3 quiver operations on it. Okay. So the first one is a gauging operation. So what we do here is simply take UM alpha, split it into 2 flavor nodes, R alpha and M alpha minus R alpha, and then gauge this R alpha node. first one. The second one is, again, take the same thing, split it, and now add some extra matter at the flavor node R alpha. Okay, so this is I'm not producing anything. I'm at this point just discussing operations on the quiver itself. All right, and then the third one is identification operation. So assume that there are two such nodes. I split each one of them, and there's an equal rank component which I identify. Okay, good. Are the operations clear to everyone? Okay, so now using these three quiver operations, I define something which I call an elementary S-type operation.
Actually, I do have a question.
Sure, yeah. Go ahead. Yes.
So is the theory different here now, or did you just basically rewrite the global symmetry? Like,
so when I did gauging, then
so
of course.
Okay, where's the gauging? So did this?
So the first one, I mean, these are independent operations.
This one is clear. This one is clear. I meant the next slide.
Yeah, I'm not doing anything here. I'm just changing the rewriting the global symmetry in a different.
Okay, yeah, okay, good. Then everything's clear. Thanks.
So just to understand exactly, so you mean because your class U theories, they are really quivers with a G. And so here you didn't change the quiver, but you changed what is the G, the global symmetry. Right?
That's correct, yes.
Okay, okay.
But again, it's not really changing the global symmetry, but
No,
just you identify
just
something.
the G, the label G that you put next to the quiver. This G sub. Right.
Mm.
Yeah, I'm messing with the background. Yeah, so okay, so the background that you can turn on is only the Cartan. Now what I'm saying is that you identify the Cartan in two different ways. It's either the Cartan of UM alpha versus the Cartan of UR alpha times UM alpha minus R alpha.
Yeah, sure.
And it looks stupid, but the next slide will clarify why I'm doing it.
Okay.
Okay, so the reason why I'm doing it is because I want to define something like called an elementary S-type operation. So this is defined in this line, which basically means that you take a theory X of class U, you operate the identification, you operate or not operate, N1 can be 0 or 1. You operate any number of identification and flavoring operations on it, followed by a gauging operation. Okay, so at the end you're always gauging. So what that means is that I can, for example, let's say take this, right? So here I identified first. Now I can gauge this UR alpha. Now this now produces a theory which is different from the original one. So here I'm not just playing with the flavor symmetry. Okay, so here I have actually produced a new SCFT, like generically at least. So the name S-type comes from the fact that if I didn't have flavoring or identification operation, and the gauging was just a U1, then this is the S operation of Witten, the SL2Z operation. So this is a generalized version of that. But it does the same thing. So that S operation also is supposed to produce a new SCFT starting from an older one. And that's also what this S-type operation is doing for us. Okay, so now just from the definition, you see that there are 4 types of elementary operations, depending on in what combination you take the identification and the flavoring operation. So the first one is, of course, pure gauging, where you just pick nothing else. Then there's flavoring gauging, identification gauging, and the fourth one where you both identify, flavor, and then gauge. Okay, there are 4 types of operations like that. So that corresponds to N1, 0 and 1, N2, 0 and 1, and so on. Okay.
What's the label, the subscript P?
Yeah, I'll state in a second. Yes. So P is telling you, that's a very good question, actually. Thanks for that question. So P is telling you how you're identifying the Cartan of UM with UR minus UM minus R. So there's a choice involved of which masses you pick, okay? And so this is determined by a permutation matrix of order M. And so P is basically that data, okay? And it turns out that that data is important for finding out the dual of this operation. So, which I'll explain now in a second. All right. So now a generic S-type operation is a combination of such elementary operations. So, and each operation is again labeled by alpha at the particular flavor node at which the operation happens, and this permutation matrix P. Okay, so this is the entire data of a generic S-type operation. Okay, so is the definition clear? And then I'll proceed. Good.
Yeah, I think an example will definitely help, but I guess.
Yeah, so the examples are coming.
Yeah, perfect.
But here I'm not even talking about, at this point, I'm not even talking about any mirror symmetry or anything. This is just a quiver operation. So if you, one example would be like, let's say you just take this one and promote this R alpha to a gauge node, right? That's an identification gauging operation. Okay. Similarly, if you go back here, this is just a flavoring operation. Now promote this R alpha to a gauge node. So then this is a flavoring gauging operation. So yeah, this is like probably the simplest example that you can think of. So yeah, so I'm not doing anything fancy. I'm just defining some quiver operations. But the important thing is that since there is gauging involved, you will produce a new theory from the old one. Okay, that's the idea. Okay, so now why am I saying all this? So I'm saying all this because I want to construct new mirror pairs given older ones. Okay, so remember the initial problem was that you gave me a very complicated quiver, and I was supposed to find out the 3D mirror of them. Okay, that was a 3D problem that we started with. Now, to answer that question, my strategy is start with two theories, a pair of theories which are known, which are simple, which we know the mirror. Which we know how things map on both sides, and the mirror symmetry is completely understood. Now, if I can generate this more complicated quiver from one of them using these operations, then all I need to figure out is what is the dual of that operation. Okay, and then at the end of it, I'll have a new pair of theories starting from this older pair. So that's the basic idea that we're going after. So anyway, let me discuss the thing. So consider a pair of good Lagrangian theories, X and Y, with X in class U. And then X and Y are mirror-symmetric. Now imagine subjecting X and Y to this S-type operation, where the map O that I constructed acts on this theory X. So as we discussed earlier, it gives some theory X prime. Okay, but the same map also acts on the dual theory Y. Okay, and gives some theory Y prime. Now, by the virtue of the construction that I just presented, you know that X prime is a Lagrangian theory because it was just a quiver operation. So the operation produces a Lagrangian theory. It's not clear that on the other side, you'll get a Lagrangian theory. Okay. So that's something that you need to figure out. Okay. So the way to do this is to basically realize this operation in terms of some supersymmetric observable and try to read off y prime. And in general, this is a difficult task. In general, if the gauging involved is non-abelian, then there's no guarantee that y prime is a Lagrangian theory. In fact, in many cases, it turns out that it's not a Lagrangian. However, sorry, 1 second. Yes, so this I already said. However, there is a very important special case where y prime is guaranteed to be a Lagrangian theory, and that is when the gauging operation is just a U1 operation. So you have identification and flavoring followed by a U1 gauge. Okay. And this is all we'll need for today's discussion. Okay, we'll already see that that's powerful enough to tell us a lot about Argyres-Douglas theories. Okay, so then let's just summarize what I just said. So you start with a pair of linear quivers, X and Y. You can implement a sequence of S-type operations, which in our case will be abelian S-type operations, ensuring that X prime is good, it remains a good theory at every step. And then you can read off the dual Y prime from the partition function. And as a result, you started with a pair of theories X and Y. What you end up is another pair X prime, Y prime. Okay. All right. Are there any questions?
So in your previous diagram, you have yes, here you have O alpha and O tilde alpha, but the theory and its mirror don't have the same symmetry. So I thought the alpha was labeling the particular U. UN.
That's correct. So it's defined in terms of X. What O tilde alpha is, I mean, they have the same symmetries, of course, but it's not visible in the UV.
On the other side. So
yeah, exactly. It's not visible in the
flavor node.
Say it again.
You don't have a flavor node with the index alpha on the magnet.
That's correct. So you should read this as O alpha P tilde over the whole thing.
Okay, so it will not be the same operation on that.
It's not the same operation.
Okay.
So that's why it's the tilde. So this is actually, well, it's the same operation at the level of the SCFT. It's the same thing. But here I'm distinguishing the map of Lagrangians because that's what I want to derive.
Okay.
So O is a map in the space of, let's say, Lagrangians, and then O tilde is a map in the space of dual Lagrangians.
Yeah, and as you said, so if it's non-abelian, then it is this O tilde map that you have not described yet. This is the one that, if it's non-abelian, is not guaranteed to give a Lagrangian.
That's correct. Yes, exactly. Yeah, and that's why you need to do all this song and dance about supersymmetric observables. Otherwise, if it's just for an abelian thing, then you can just do it at the level of the Lagrangian.
Yes. Okay. Thank you.
But for today's talk, we're not going to do anything non-abelian. We're just going to stick to abelian stuff, and we'll see that already is good enough for these sort of theories, Argyres-Douglas theories. Okay. Other questions? Say it again.
Anindya?
Yeah.
Hi. Sorry. So for the non-expert, could you just, in a few words, explain in what sense X and Y are mirrored?
In what sense X and Y are mirrored? So
yeah, what does it mean for X and Y to be mirrored and for X prime and Y prime to be mirrored? What are the relations between the observables?
Oh yeah. So it's an IR duality with a special property that the Coulomb branch of X is isomorphic to the Higgs branch of Y in the deep IR, and again vice versa. The Higgs branch of X is mirrored to the Coulomb branch of Y in the deep IR. Okay,
thanks.
And so X and Y are mirrored to each other, and X prime and Y prime are mirrored to each other, but X and X prime are not mirror or dual to each other in any way. So in another way of saying it is that X and Y basically, in the IR flow to the same SCFT, and X prime and Y prime flow to the same SCFT in the IR, but a different one.
I see. And is there a way of understanding this in from a symmetry in 4 dimensions. So you started from this in 6 dimension. You started from this serial in 6 dimension compactified on C, and then well, that's what you wanted to do basically. Maybe you haven't told us that yet, but
yeah. So this I'm still talking about generic 3D mirror symmetry, which doesn't.
So you will come to that.
Yeah. So this is still like, so there are two parts of the problem. The first part is the class S construction and knowing a certain 3D mirror, which corresponds to this Argyres-Douglas theory. But then there is a completely 3D question of understanding the mirror of that theory. So I'm right now just discussing the 3D problem without any reference to Argyres-Douglas theories at this point.
Okay, thanks.
All right. Okay, other questions? All right, so now if we restrict to abelian S-type operations, then things become much simpler. So these 4 elementary operations that I just described can be readily understood as at the level of the quiver. And the dual operations can be explicitly written down. So let's list them. So the gauging and the identification gauging operation is just involves ungauging of a U1 subgroup of Y. So this is reminiscent of of Witten's SL2Z, the S operation of Witten's SL2Z. I mean, you gauge on one side, you ungauge on the other side, and then the flavoring gauging and the identification flavoring gauging. These result in the following quiver, which I'll describe. So the quiver, the resultant. So remember, this is Y prime. Okay. So it has 2 subquivers. It has a quiver Y and a chain of U1s. Okay, so these are the 2 subquivers, and these are connected by a single abelian hypermultiplet, which is charged 1 under this U1, and can have a charge Q under, and is described by a charge vector Q under various unitary gauge groups that Y may have. Okay. So Q comma P describes the charges of this abelian hypermultiplet. So this is the general structure of the dual theory. Okay. Now exactly what the charges are, which nodes it connects to, that is dependent on the particular problem at hand. But the general structure of the dual theory is simple, and it's just this. Okay. All right. So then we arrive at this result that suppose I have a quiver gauge theory X prime, which is related to another quiver X by a sequence of these abelian S-type operations. And X is known to have a Lagrangian mirror. So then, by this construction that I just described, X prime is guaranteed to have a Lagrangian mirror. Okay, so you can just look at the quiver X prime and say that it must have a Lagrangian mirror. Okay. And in addition, you can also say what this mirror, what the general properties of this mirror should be. It will only have unitary gauge groups because that's what you started with, and it will probably have matter in different representation, but it also will have a certain number of those abelian hypermultiplets that I just drew. Okay. So this will be the result that will basically help us to crack the problem of Argyres-Douglas theories. Now the statement is that the class S 3D mirrors, which I was discussing a few slides ago, can be engineered by a sequence of abelian S-type operations from linear quivers with unitary gauge groups. So you can identify the theory B that I had with X prime and A with Y prime. B is the class S mirror. So you you obtain the class S mirror by a series of abelian S-type operations from some linear quiver X. And by the theorem that we just proved about abelian S-type operations, you know that Y prime must be Lagrangian. So now we'll see some explicit examples of this construction. So let me pause here and take questions if there are any. All right. So let's begin with the example of A, A type theories. So the 3D mirror from class S is well known for these guys. It's a complete graph of S plus 1 vertices with edge multiplicity P. So the simplest non-trivial example is S equals to P with a generic, S equals to 2 with a generic P. So a quiver of this form. So I have, factored out one of the U1s, which leads to this. Okay. So now, how am I gonna? So the idea now is to take this and ask whether this can have a Lagrangian. Okay. So I want to figure out if this one has a Lagrangian mirror, if this quiver has a Lagrangian mirror, using what we just learned in the earlier slides. Now, you can check that this could be done in the following fashion. So suppose I start with a U1 theory with 2P flavors. Okay. And I divide the flavor symmetry in this fashion, and then I take the UP factor and break it up into PU1s like this. And then I identify first, add extra P hypermultiplets, and gauge the U1. Okay. So this is a single identification, flavoring, gauging operation. Okay. Is this clear? Like what the operation is? All right. So it's a single operation from which you can go from a linear quiver to this quiver of interest. But now we have already proved that the dual of this operation must give you a Lagrangian theory, right? And we even wrote down the general structure of that Lagrangian theory. So let me show it to you without further ado. So this is, as Julius was asking for, first sort of example in this category that works. So you start with U1 with 2P flavors, which is dual to this abelian gauge theory. So you do the identification flavoring gauging operation, and the effect of that is the attachment of this tail of U1s to the pth node in the chain. Okay, so there's a node P here, and the effect of this S-type operation is the attachment of this this tail. Now note that there is no abelian hypermultiplet here, and that's because the abelian hypermultiplet in this case is just a trivial bifundamental. Okay, so this is a special case. We'll see in later examples that's not the case. Okay. So then this guy is the Lagrangian of A2, A3P minus 1. So the Higgs branch of this guy realizes the Higgs branch of the 4D Argyres-Douglas theory of this type. Okay. So in an earlier paper, Amihe, Hanani, and Del Zotto basically computed the Hilbert series of these guys, the Coulomb branch Hilbert series of these guys, which will now be given by the Higgs branches of this guy, Higgs branch Hilbert series of this guy. So it's kind of really nice to see how the how the flavor symmetries become apparent and manifest on this side. So if you look at this theory, this is an SUP cubed times a U1. Okay. Now, in this theory, you can see that there's a chain of p minus 1 balanced ones. That's an SUP. There's another SUP from here, and another SUP from here, and a single U1 that's unbalanced. And so it's a very nice way in which this Coulomb branch symmetry is realized.
Very cool mirror pair.
Sorry, what?
Very cool mirror pair. I like it.
So yeah, so the nice thing is that, not only do you have a theory, but it's also a theory in which this Coulomb branch symmetry becomes very manifest. And this we'll see also in more complicated examples later on. Okay. And one of the tests you can do is that you can compute the Higgs branch Hilbert series of this guy and compare with Ami's results, and you see that there's nice agreement. Okay, but you can continue doing this for higher S and higher P, and it works seamlessly, and it can be extended to the A-D-type Lagrangians, which also can be worked out in exactly same kind of fashion. That means that the exact mirrors are different, but the construction is exactly the same. So, all right. So now let's get to more complicated objects. Which okay, now let me actually pause for a question before I go there. Are there any questions? All right. So now let's discuss the DP-SUN family. So for the P less than N, this is the Quiver. This is the class S mirror. Now the details are not important, but the general structure of this thing is important. So you see that the mirror has two distinct subquivers. One is a linear quiver of this form, and the other one is a complete graph of certain number of vertices, and there are a bunch of bifundamentals connecting them. Okay, so all these numbers x, p, m1, and 2, they can be read off from these two integers p and n. So that's the basic idea. And again, I have to decouple an overall U1, which I have done. So this is the class S object. Now, question is, how do you construct such an object from a given linear quiver using the class S operations? And that's done in the following fashion. So look at this object. This is a linear quiver. I again play with the flavor symmetry in this fashion and break up the M1s into M1 U1s, the M2 into M2 U1s, identify flavor and gauge. Okay, that's the first step. And then the next step, I again isolate a certain number of flavors, identify flavor and gauge to give the second one. And I can just continue doing this indefinitely to generate a generic quiver gauge theory of this form. Okay. All right. And similarly, the same thing could be done for p greater than n. So again, the basic structure of this is the same. It is a linear quiver and a complete graph coupled to each other by these bifundamentals, certain number of bifundamentals. Okay. So it turns out that that these 3D mirrors from class S can be engineered from a linear quiver by a certain number of identification flavor engaging operations, always. And what is important is that these operations are all abelian operations, so that we can use our theorem that we stated before and write down the duals of these operations. So this allows you to say certain general things about the mirror, like the mirror of the mirror. So firstly, it tells you that the circle compactification of DP-SUN must be Lagrangian. So this just follows from the properties of abelian S-type operations that we presented. Secondly, it tells you that the Lagrangian must be such that the gauge group is a product of unitary factors. And in addition to fundamental and bifundamental matter, the quiver will involve several hypermultiplets, which are only charged under certain U1 subgroups of the unitary factors. Another way of saying it is that it will have only hypermultiplets, which we will have several hypermultiplets, which transform in the determinant or anti-determinant representation of various UN factors. So the DP n-1 SUN family is another infinite family that can be analyzed in the analogous fashion. So there's again very close parallel between these descriptions. So now let's look at a concrete example from this class. So let's consider a DP-SUN theory where P equals to 4 and N equals to 6. So this is the mirror. It's a linear quiver, as you can see, coupled with a complete graph with 2 nodes, where the edge multiplicity is just 1. Okay. So now if you decouple the overall U1, this is the non-ADE-type quiver that you get. Okay. So again, we ask the question whether this has a Lagrangian mirror, and the answer is yes. So again, the starting point is a pair of linear quivers, X and Y. You identify these two, add a flavor, and gauge it. And the result on the other side is just adding an abelian hypermultiplet connecting 4 and 1. Good? All right, so then that allows you to write down the 3D Lagrangian for D4SUX, which is just this. So this would therefore realize the 4D Higgs branch corresponding for the corresponding Argyres-Douglas theory. Okay. And okay, let me pause here and take questions. Sorry, 1 second. Okay, so this is the simplest example in the DP-SUN theory where you can do this. Now let's move to a slightly more complicated example where P is 9 and N equals to 3, so P is greater than N. So here again, this is the class S mirror, and you see that this is again consists of 2 subquivers. This is a linear part, a linear quiver, and coupled to, the linear quiver is like 1, 2, 3. It's like TU3, and there's a complete graph of 3 nodes and edge multiplicity 2 that's coupled. Okay. And you can decouple one of the U1s and get this X prime. Okay, so then again, can I compute the mirror of this? Yes, I can. So the starting point is the TU3 theory, which is self-dual. I start with this U1, I flavor it and gauge it. that produces this theory on one side, and the dual could be computed. So remember, it was a TU3 theory. So the effect of the dual operation is just attaching this segment, this chain. Okay. And then again, what I do is that I identify these three flavor symmetries, these three flavor nodes, flavor the identified node, gauge it, and I get on the dual side this object. So there is something that connects now this node and this node. So this is the effect of the dual operation. Okay. So you can see at each step what you're doing on one side and what you're doing to the dual side. Okay. So here you see that there is indeed an abelian hypermultiplet that appears, and the charges are given and so on. Okay. So and this you can basically systematically do for the entire series of DP-SUNs and and also the DPN -1 SUNs. Okay. All right. Again, here you can check that the Coulomb branch symmetries actually map nicely. The Higgs branch symmetries also. So here, the SUs you can count. So it's an SU2 times SU2, and there. Yeah. So if you count the SU2s, and which I'll do in a sec, you can see how they nicely agree. All right. Okay. Any questions up to this point?
So I have a question. So for maybe it's the next slide. I was about to ask for the quivers with U and SU, and if you have
it's coming up. It's coming up. Yes.
Okay, so then it's equivalent in some cases. Okay.
That's correct. Yes, it's a proposed IR duality, which I have checked with some certain things. Yes. Okay. Thanks. I'll come to that in 1 second. But firstly, is the construction clear? That's what I want to first ensure. So it's a very straightforward thing. So once you have established the dictionary, then you can basically just run it through, and it's a constructive thing. It spits out the dual. All right. So now that we have learned how to compute the duals, let's address the question that was asked. And we know that there is another Lagrangian for these DP-SUN theories that come from the 4D construction of these guys. So what happens is that you can consider a certain partially weakly coupled description of these DP-SUNs. So this is in terms of certain isolated SCFTs, which are these curly DQs. So these curly DQs have a flavor symmetry, which is SUN times SUN minus small n times U1. So this guy and this guy has an SUN minus n flavor symmetry. All I'm doing is that I'm gauging that with a SUN minus n vector multiplet. Okay, so it's a description in terms of isolated SCFTs and vector multiplets. So that's why it's a partially weakly coupled, not completely weakly coupled. Now, when you take such an object and you compactify on S1 and flow to the IR, what you get in 3D is a chain of SUNs. What you get in 3D is a structure like this, T1, SUN, and so on, where the SUs are vector multiplets in 3D. I mean, they just come down without any change, while these isolated SCFTs become linear quivers with unitary gauge. Okay, and this line in the middle just becomes certain bifundamentals. Okay, so that's the basic structure of these Lagrangians that were suggested by Close et al. And others. Okay, so then comparison with our results would suggest that we have an IR duality between these two sets of theories. So on the one side, we have this linear chain of unitary and special unitary gauge groups with fundamentals and bifundamentals. On the other side, we have a generically nonlinear quiver involving only unitary gauge groups decorated with abelian matter in addition to fundamental and bifundamental vectors. Okay. Now, the most elementary example of this is this following theory, which has nothing to do with any DPSUNs, but it's just something that is the most elementary example of such a duality. So on one side, you have SUN with 2n-1 flavors. On the other side, you have a UN-1 theory with same number of flavors, but additionally with a single abelian hypermultiplet of charge n-1. Okay, and you can check that these are mirror dual to, I mean, these are, sorry, not mirror dual, these are IR dual to each other by checking that the partition functions agree, for example. And you can compute, for example, the Higgs branch, the Coulomb branch Hilbert series of this guy. And you'll see that there is an emergent U1 symmetry, which maps to the U1 topological on this side. Okay. And this is pretty interesting because if you take SUN with any other number of flavors, so let's say you take 2n or 2n plus 1 or anything else, that does not have that emergent U1 symmetry, only this guy has. And that is what maps to the U1 topological on the other side. Now, for every P and N of DPSUN, this comparison will give you an example of IR duality of this type. So there's an infinite class of IR dualities that you can write down just from this equivalence. And the two examples that I discussed, correspond to the following dualities. So for D4 SU6, this is what I had, and this is what the USU Lagrangian looks like. And the D9 SU3, that's a little more complicated, but these are the two dual theories. So I want to emphasize that this is not mirror symmetry. So tau and tau check are not mirror to each other, but they are IR dual, which means that the Coulomb branch maps to Coulomb branch, Higgs branch maps to Higgs branch. Okay. Now, what is really interesting is how the Coulomb branch global symmetry becomes manifest in the unitary curve. Now, one of the issues that was dealt with not in the Close et al. Paper, but the paper by Giacomelli, Beccaria, and others later, was to figure out from a Hilbert series computation what is the true Coulomb branch symmetry of these guys. Okay, because if you naively try to compute, you'll get a wrong result. So you have to, just from the observation, you have to figure out the rules for this for the Coulomb branch symmetries of this guy, which is different from a linear quiver consisting of unitary gauge groups. Okay, so for example, just to give you an example, this guy has a Coulomb branch symmetry of U1 cubed. Okay, one of the U1s is emergent. So there's U1 from here, there's U1 from here, but there's also a U1 from here. Now from the unitary quiver, this becomes manifest. So there are exactly three UN. There are three unitary factors, and there's U1 factor for each one. What happens in the second example is even more radical. So you see here one balanced object, another balanced, but the true global symmetry is SU2 cubed times U1 cubed. Okay, but that becomes completely manifest on the other side. So let's count. So you see, let's see. So this one is balanced. This one is balanced. This one is balanced. So that gives you an SU2 cubed. And there are three unbalanced ones. That corresponds to U1 cubed. Okay. So this is a feature of these unitary quivers, that you don't have to basically do any Hilbert series computation to know what the Coulomb branch global symmetry is. You can just simply read it off from the quiver itself. Okay, is this clear? Or should I?
Anindya,
Yeah.
if you fix the Coulomb branch and the Higgs branch, you would have just 2 quivers for each case, or can you construct the third one, which will produce the same pair?
What do you mean? I don't understand.
So if you have multiple SU nodes, then probably you can produce multiple quivers where you delete a SU node, you change it for a U node. So here you have 2 quivers which have the same moduli space. So could you in general have a class of, let's say, n quivers which have the same moduli space? I'm guessing that this appears when you have multiple SUs on the left.
Yeah, so you can choose to implement this. Yeah, you can choose to replace one of the SUs by a unitary quiver, and not the others. I guess yes, you can do that. Yes, but right. So I'm not claiming that these are the only 2 Lagrangians that you can possibly write down. I mean, obviously, you can also write down a bunch of stuff which are just field redefinitions, but those are probably not what you're talking about. So yeah, so you can do that. You can if there are multiple SUs, you can choose to replace one of the SUs with unitary gauge group and not the others. But that is not going to be the quiver that you get from this S-type operation. So it'll be a different thing. So the S-type operation is guaranteed to produce a quiver which has only unitary gauge nodes and nothing else.
Yep.
Yeah. All right. But in those kind of quivers, this problem of having to read off the true global symmetry, the Coulomb branch global symmetry, will persist. I mean, you cannot read it off from the quiver off the bat. I mean, you'll actually have to compute the Hilbert series and then observe from that computation. The advantage of this unitary quiver is that you just read it off from the quiver.
Yeah, sure.
Yeah. All right. Other questions? All right. So that's pretty much what I had to say, in terms of content. But let me just quickly close by saying a few directions that I think will be significant for this. So firstly, one needs to say what is the maximal set of Argyres-Douglas theories which admit 3D Lagrangians of this form, which means they're only built out of these unitary gauge groups and this extra matter. So I already told you about the A, A family, the A, D family, the DPSUNs and the DPN-1 SUNs, but this probably extends beyond that, and it's just needs to be worked out as to what is the maximal set of such families that admit 3D Lagrangians of this type. The other interesting question is about 4D 2D correspondence. So we know that in that correspondence, the Higgs branch is constructed as associated quiver of the vertex operator algebra. So now we have these 2 realizations of the Lagrangian we have a realization of the Higgs branch as a 3D quiver. So the question is, can I say anything interesting about the vertex operator algebra from the quiver itself? So that's a question. The third one, which is a work in progress, is mapping line defects across mirror symmetry as well as this new duality. So some partial results were obtained in a paper that I wrote in December, but there's a lot to explore in that direction. Yeah. Sorry, was that a question?
Maybe there is a couple.
And then extending to USU chains, which do not arise as reductions of DPSUNs or Argyres-Douglas theories. I mean, you can write down chains of U and SU, and you can ask the same question, whether they have IR duals of this form. So that's something that that's a completely 3D question, and That's probably worth exploring. And the final thing, which is also probably worth thinking about, is that whether these Lagrangians could be realized as fixed points of some 3D n equals to 2 flows, just like the Argyres-Douglas theories are realized as fixed points of some 4D n equals to 1 flows. And it would be interesting to understand what are the constraints on these kind of constructions. All right, I think that's pretty much all I had to say. Thanks for your attention.
All right, great. Let's thank Anindya. Do we have questions? Ooh.
Silence. Oh, yes. Sorry, I stopped sharing. Sorry, it's my bad.
No worries, no worries. Yeah, so
we did ask questions.
No, of course.
No silence.
Huh?
There was an interest from India.
Yeah, of course. So these dualities really look extremely powerful to produce 3D mirror pairs in general. How systematic can you, like, how simple is it to do them for like some crazy quivers?
No, I mean, like
these these S operations, I think you call them.
Yeah, so like these ones, for example, let's say, let's look at the generic things, like these guys, for example. I mean, to me, like if you told me 2 years ago, I would say these are crazy looking quivers.
Yeah, exactly. That's what I'm saying. So this opens a whole new.
Exactly. That's the whole point of this. Yeah.
So you might. It's pretty easy.
It's pretty easy. It's almost numbingly easy.
That's good.
So it's just it's just simple. It is something that you can even do at the level of the Lagrangian. I mean, it gets cumbersome, of course. So doing it using some partition function is better. But in principle, you can just write the Lagrangian and just do it step by step. And it's actually that easy. So yes, I mean, a huge range of things could be opened up.
Yeah.
What's funny is that for Argyres-Douglas theories, it's just abelian S-type operations. Like you don't even need to do anything non-abelian.
I have a question on this point. Sorry, my camera I think doesn't work anymore, but I hope you can still hear me.
Yeah.
So do you have? I mean, can you apply these methods for quivers in which you have loops of non-abelian nodes? So here, for instance, on the examples on the screen, you have a line of non-abelian nodes, and then there is a cloud of abelian ones. But
that's correct.
So what happens if you have a loop of non-abelian ones? Is there some problem there or something happening?
No, there's no problem. I mean, you can implement the whole thing, but the dual is not easily readable, like in the abelian case. I mean, you actually have to do the computation, like
But you mean that the dual would still be Lagrangian?
No, it's not guaranteed, right?
Okay, not guaranteed.
So so it depends on how you're generating it. So if you can, so the object can have, I mean, the final answer can have a bunch of non-abelian nodes. What is important is that when you generate it from a linear quiver, are you using abelian S-type operations or non-abelian S-type operations? So if you generate a non-abelian theory using abelian S-type operations, then everything is fine. It's like the dictionary. Now, if you are having to gauge non-abelian flavor symmetries, then you have to, actually compute it and see if there's no guarantee that it will be Lagrangian, generically speaking.
Okay.
So then you actually have to compute and see whether it's Lagrangian or not.
But there are examples where it works, where you have a quiver which
that's correct,
has cycles with non-abelian nodes, and you still find a mirror, and it's also Lagrangian. There are examples of this.
Oh, like these ones, like of this form, you say?
Yeah, something like this. But let's assume you take this example here, and you replace all the ones by 2, for instance.
No, I mean, I haven't done that calculation.
Okay.
I haven't done that calculation, but the simplest thing you can do is a circular quiver, for example.
Yes, but okay, the circular quiver, this one is a bit too simple.
That's correct. Yes.
Okay.
So I mean, so yeah. So if you're asking me if I've found an example of a new 3D mirror pair using non-abelian, gauge symmetry. I'm sorry, non-abelian gauging operation, which is not covered by string theory constructions. Then the answer is no. I haven't found anything yet.
Mhm.
But again, there's no systematic way to look also, right? I mean,
Okay.
it's a random thing. I mean, for the Argyres-Douglas theories, I know because there's a classless construction.
Yeah, no, of course.
Right? So that's a problem. So if you have a very interesting non-abelian quiver, you can try to generate it using this technique and see if you get it.
Mm-hmm. Okay. Yeah. Thank you.
Okay, do we have more questions?
Is there a way to arrange the theories in a certain order?
Say it again. I missed that.
At the moment, we have a set of operations, and it generates some pairs. But is there a way to make any order in the set of theories that we have? Some kind of, arrange them into families, some classification, I don't know. Some structure.
I mean, you can think of classifying them in terms of number of loops, for example.
Mm-hmm.
Number of loops, and if you have what are they called? So Walsh has a name for these kind of things. So basically, loops and handles.
I see.
So yeah, so you can think of. I mean, that's like probably one of the things you can do. I don't know from the perspective of graph theory if that's like a complete set or not, but that's something that you can think of. So you have n number of loops, and you have m number of handles, and you try to construct whatever you can with that. So I basically I basically restricted myself in my earlier papers, like small number of loops and very small number of handles, but the number of nodes in the handle could be large. So that's one way of arranging things. But I don't know if there's any physical motivation for that.
Well, the next question will be whether you could find Argyres-Douglas theories which are not in the current classification.
That's correct, yes. That's correct. But it seems that, so I was reading through this recent paper that Dan Shi wrote, where he is writing down the most general form possible for these kind of theories, that the 3D mirrors from class S. When it exists. I mean, it may not exist in all cases, but when it exists, he gives a form. And the form is still the same form as this, it seems. It still has like various subquivers. The subquivers could be linear quivers, and then they are connected to these sort of complete graphs. And if that's indeed the most general thing, I haven't checked the computation, so I don't know that for sure. But if that is true, then what I said just carries over straight away. So there's no problem.
But no additional Argyres-Douglas theories that we are not aware of.
No additional what? Say it again.
Argyres-Douglas theories that we have not seen up to now. That's the question.
That's the question. Oh, that's very interesting. Oh, okay. Okay, that I don't know. Okay, that's a very interesting question. So how would you check that? Let's see. Yeah, so for example, I mean, one thing that you can do is that take an arbitrary linear quiver and an arbitrary complete graph and connect them with bifundamentals, where let's say these are different. These are not M1 and M1, but let's say these are like M, N, and P. So then you have produced something that is not class S 3D mirror of any Argyres-Douglas theory, known Argyres-Douglas theory. Okay, but that is something that you can totally compute using these methods, and you can ask, you can compute the central charges of that object, like supposed central charges of that object, and ask if that matches to any SCFT that one can hook up in 4D.
Yeah.
So that's a game you can play. I mean, it's totally possible.
Mm-hmm. Now, another question is whether, so I think it's quite clear that those will not be slices in an affine Grassmannian of some algebra.
Almost nothing is, right?
Most are not, you say.
Yeah. So this is
So
it would be an extreme coincidence if this is what you get.
Yeah. Well, okay. So let's ask the question the following way. How much has been done to compute the Hasse diagrams of the moduli spaces?
Nothing, as far as I know. I mean,
I see.
Yeah.
So that's also an interesting.
Exactly. Yeah. So
figure out.
Okay, before we go into the post discussion, maybe we can thank Anindya one more time.
okay.
And I'll end the recording.